All right, I think we're ready to start. I can't really tell if we're all in here or not. Is everyone in here, Stephanie?
Yep.
Okay, all right. Well, hi, everybody. My name is Nate Lena. I'm a fourth-year radiology resident at the University of Pennsylvania, and this is the first journal club in our sort of monthly series we're putting on for the Artificial Intelligence Subcommittee of the RFS section. And I decided to go with a natural language processing paper, showcases some pretty cool things. The paper's called Automatic Fully Contextualized Recommendation Extraction from Radiology Reports. Oh, skipped one. All right, so I'm just going to show you how we're going to go through this. I'm going to present for about 20 minutes or so, and after that, we'll have ample time to discuss the paper, go through things. I wanted to mention that this presentation is recorded and will be online on the website somewhere. And here's like a Twitter handle for us that you can use as well. This is our ACR RFS AI subcommittee. There's me in the bottom middle. You'll see a bunch of these other people presenting through the year. Bottom right is Dan Cohen. He's sort of our ringleader this year. All right, so I'm just going to briefly talk about the paper that we're going to talk about today. It's from the Journal of Digital Imaging, which is the journal for the Society of Imaging Informatics and Medicine. Pretty cool society, has some cool conferences as well. And we're going to talk about the authors here. We have some of them with us today. We have Jackson Steinkamp online with us. He's the first author. He's a second-year resident in the primary care internal medicine residency program at the University of Pennsylvania. And then Tessa Cook is the last author on the paper. She's an assistant professor of radiology at University of Pennsylvania. She's also the chair-elect for the board of directors of Society of Imaging Informatics and Medicine. She's actually on maternity leave for the last 3 weeks or so. And she said she tentatively might show up on the chat later. So we'll see if she could answer some questions for us later. So before we sort of dive into the paper, I just wanted to give a little bit of background information in case you're not that familiar with sort of AI methods or natural language processing. So NLP is a subfield of AI. It interprets not only text, but also sometimes spoken language as well, but most commonly text. It can extract text, classify text. It can also like generate text. If you're at RSNA, you might have been able to see some products that can like automatically generate an impression section. That's like an example of like a text generation NLP. But in the whole umbrella of AI, as you can see in this diagram in the lower right, NLP is kind of inside AI. And then things like machine learning or deep learning, which you would commonly associate with image-based AI, there are also things that can be used in NLP as well. So there's a lot of different types of natural language processing, and models kind of have different bases. So some of the more simpler ones that have like lower performance would be rule-based. Kind of analyzes text and extracts specific words or phrases out of text based on how you set rules in the program. There's some statistical methods that kind of use like frequency algorithms of words to assign meaning. And then we have like the machine learning and deep learning models that use classifiers that can be trained to interpret more sophisticated meaning in text. They have pretty high performance. Some of those would be like neural networks you've probably heard of before, support vector machine. And then the newest sort of thing that's come out in the last couple of years are called transformers. I'm not that familiar with them because I don't have a huge computer science background, but they have very high performance. They've been doing pretty well in the recent papers in radiology. But the most common one is BERT, which is bidirectional encoder representations from transformers. So NLP is applied in radiology, mainly because the product of radiologists is the radiology report. So it's like a text document. There's a lot of cool things people have done with them. identifying clinical findings, quality and safety sort of projects or tracking, just extracting different things for like clinical research databases, and then sort of text generation things like I said earlier. So now after I give that brief background, I'm going to dive into the paper here a little bit. Hopefully you guys were able to read some of it or all of it, or at least kind of get a gist of the paper. But so in the introduction, we're talking about what is the problem that this study addresses. So communicating follow-up recommendation to clinicians is kind of a common thing. The radiologist addresses a problem. Prior works have had limited performance, or they've only kind of done one thing. For instance, it could be a paper that's like reviewing thyroid nodule recommendations, only working on thyroid reports. It could only be picking out like one phrase or something. This paper is going to try to do more than that. But more automated tools can like give more information or come from one algorithm instead of like a bunch of small pieces. And so in this paper, they're going to try to extract the type of follow-up, the strength of the recommendation, the timings, and the condition for recommendation. And they're going to try to do all that in one deep learning model. So before we even start talking about model or training or anything like that, we got to talk about where we're getting the data set. So these are a little bit over 2,000 radiology reports, random reports, all from a single health system. So this is mammography, CT, X-ray, ultrasound, all sorts of things, not just one single report, different structures and different templates as well. And then the sort of primary objective of the study is what are all the recommendations in these reports? The other questions that's sort of downstream from that top level question is what's the time period? What are the stated reasons for the recommendation? Under what conditions should the recommendation be performed? All of those questions are going to be approached with the named entity recognition and the NLP algorithm and model, which they talk about labeling here a little bit in a second, the annotation. And then the secondary task is the classification task, was sort of just like a yes or no. And that's what is the strength of the recommendation and whether there's the recommendation is negated. So now that you have your radiology report text and you have like your goal of what you want to do, we have to start like working with the text. So the text is tokenized, which essentially is the sentences are all sort of broken up into individual words, and then manually annotated through a web application. And here's a figure from the appendix of the paper that kind of shows how the manual annotation was performed. And then once you've kind of pre-processed the text a little bit, we can start talking about how we're going to work with the neural network model. So the network takes the radiology report and assigns word vectors, and then a single integer is used to evaluate the different questions being asked. The vectors in the document assign vectors to the tokens, and then the model has two outputs: the named entity recognition output and then the classification output. Okay. Give me 1 second. I'm sorry, guys. I'm actually, this is kind of a bad scenario. Hey, Jackson.
Yeah.
Could you actually talk about? I'm monitoring an MR scanner, and they were supposed to be done like half an hour ago, and I actually have to go see this patient really fast. But could you kind of talk about this, like the model and then the performance here?
Yeah, am I able to like advance slides or?
I don't know if I'm able to give you that ability.
I don't think so.
I'm just going to leave it on this because it's got a wordy slide, but I should be back in a few minutes. I'm really sorry about this, guys. Yeah, just try to like talk about the model and then these results on this page.
Yeah, sure. So basically for the model itself, we used LSTM, or short-term memory recurrent neural network model, and basically tried to kind of answer, we formulated these as kind of all separate natural language questions. And basically, for each of these questions, the model tries to predict which tokens are involved in recommendations, and then it can also be passed, like for a given recommendation, what is the desired time period for that recommendation? What are the reasons stated in the report for that recommendation? And so the model can also essentially take like a recommendation, like the text corresponding to that recommendation as an argument to the model, and basically process it that way. And then we basically assess the performance of the model on each of these different questions with some of the common metrics used in machine learning, recall, or the number of tokens, basically of the tokens that are actually in recommendations, how many does the model pick up? Precision of the model, of the tokens that the model predicts are involved in recommendations, how many actually are? And then F1 is essentially a mean of those two, kind of capturing both sensitivity and positive predictive value, or both recall and precision. Yeah, I think that's most of what to talk about here. So I will wait for Nathaniel to get back. Good timing.
All right, I'm back. I honestly can't believe that just happened. Sorry, guys. So hopefully Jackson entertained you there for a little bit. But I was talking about this here. We have the named entity task, which is sort of addressing like 4 different things. And this is a little bit more in the weeds about how things are vectorized and tokenized. And then the classification outputs, just kind of answering strong versus weak, and negation as well. And so the model chosen for this study is a LSTM, a long short-term memory architecture. It used custom trained fast text vectors on the institution's repository of reports, and also used global vectors trained on the common crawl data set. So LSTM is a little bit of a newer one. You might not be that familiar with what it is. I have a little diagram down here. You can imagine it's like pretty advanced interactions at the network level, and this is sort of a standard neural network on the bottom right. So you can kind of see that it's a little more complicated, and also demonstrate some of the recurrent neural network abilities. All right, so after you've pre-processed and you kind of made your model or have it ready and had it trained a little bit on a radiology data set, you need to do the training, validation, and test sets of the annotated data. And so in AI, and as you'll see in further journal clubs this year, the standard AI sort of workflow is making these 3 data sets. One that's going to be training the AI, and then validating, sort of tuning the parameters for best performance, and then the test set should be totally separate from those 2, and that's to determine the performance of the model. And so here's some of the major results about how much recommendations and types of recommendations that were in the study. So out of like just over 2,200 reports, there was 1,820 recommendations. You can look at this list at how many unique answers there are. That this to me kind of shows how robust the model and sort of the project is, that there's this many unique answers to the questions in the reports. Sure, Jackson, did you go over this really well, or did you have to explain a lot of background?
I just talked about like precision, recall, and F1.
Okay.
Yeah, and kind of what they are.
Okay, cool. So you explained that, and that's good to know. And so F1's kind of a score that a lot of different AI studies use, sort of comparison And in this study, they defined an exact match as in it had to exactly match, like follow-up MRI examination was the example. That would be exact match, but it said follow-up just MRI is what the model would output. That would be a partial match. And then token level is more on like similar to the partial. It would get like one or two of the words. As you can see, it does pretty well in the partial or token level. The question 1 non-exact match is sort of suboptimal at about 70%. Question 3, like pretty poor performance at like 44% with exact, but it does a lot better with partial and token. And all the rest are like pretty decent on both. And then another sort of stipulation that they tried here was whether they did a single task model or a multitask. A single task was each question had different weights or parameters, and then the multitask was just one set of weights that were altered to see if you wouldn't have to change everything, just one sort of weights in the model. Okay, and then the second task was the classification task, and is the weak versus strong, and then it was if it was negated, yes or no. As you can see, it performed very well on this task. So that was overall the results and performance. In the discussion here, the primary objective was to see if it can evaluate the follow-up recommendations for a wide variety of radiology reports, and that was determined to be a success. And they also demonstrated a single model can handle multiple questions rather than like doing multiple different NLP models to deal with the follow-up recommendations. As we just discussed, performance was a little low for 1 and 3 on exact match, but satisfactory for token and partial match. There's some things they could do with this model in the future, like more radiology findings, or like follow-up for quality and safety evaluation of completing the recommendations. So limitations in this study, all of the reports are from a single institution. So that kind of, if you took it somewhere else, maybe they do something differently, that their model, the way it was trained and annotated, it might not perform as well. That wasn't evaluated in the study. It was time intensive to label the reports for training. It'd do it manually. There wasn't like an automatic annotator or anything like that. Retrospective study. So almost all AI studies are retrospective. They're not like the large majority of them are not like live tools that are operating on real like patient scans or anything like that. And that's obviously like the highest level of evidence is doing more prospective work. And then a data set size of 2,200 is pretty good, but if you had larger data set, that would obviously make it better, better evaluation of the model. So that's the presentation for me. I'm going to let Jackson here discuss any things about the paper you wanted to say, or like any issues or things you ran into that you might not kind of get from this presentation or reading the paper.
Yeah, I mean, I think one interesting thing, just from my experience working on machine learning projects that involve like of this nature, are just that so much of it is about how you define your task and how like you, and the data labeling, you know, more than the model itself. A lot of the times, most modern machine learning models can do pretty similar performance on most tasks, at least in terms of like what you'd actually care about in terms of difference. And so like figuring out how to annotate the data efficiently is definitely helpful, because it can be a very time consuming process. But the more data you have, you know, the better these systems will perform. That's something that this project kind of hammered in even more. Okay, I see some. Should I answer questions live? Is that the best thing? Or?
Sure. I just answered one of them. But yeah, I can help you go through this.
Totally.
So yeah, go ahead and start at the top one. What's an example of a token?
Yeah, I mean, Yeah, so in natural language processing, a token is just like a word or a word-like unit. So sometimes punctuation marks are treated as their own separate tokens because they can have meaning, or like, convey syntactic or semantic meaning. In this case, it just means that like the token is every word in a document. So the token, in the results, the token level prediction task is of the tokens or of the words that are involved in a recommendation, how many does it successfully predict, as opposed to the exact match, which only counts it as correct if exactly the correct set of words for a recommendation are predicted, if that answers your question. To answer Dan's question, it took a decent amount of time to do the annotation. I mean, I did kind of a lot of projects like this in a short period of time. So I had kind of built out this custom annotation pipeline that makes it really easy to label the data and uses a bunch of hotkeys. Like I can press 1 to say it's an answer to question 1. I can press 2 to say it's an answer. So I spent a good amount of time making the annotation efficient since I knew I'd have to do a lot of projects like this. Even so, to annotate like 2,200 radiology reports probably took, I honestly don't remember how long it took, but probably on the order of like 20 hours or something like that in total. In terms of what would be a good usage of the project in real life, I would say I tend to really think like large scale descriptive analyses of things or like population level analyses of large amounts of text are really interesting. And like, especially with radiology reports, I think it's a lot of times the solution is either to have some person like manually go through every radiology report and look for instances of something to like get a population for a study. And I feel like that, if you really had good text search tools, you would be able to, generate those kinds of large scale descriptive studies pretty quickly, which I think could be pretty interesting. That's kind of my favorite use case of stuff like this, but I think there are others in terms of it, like education and quality improvement and things like that also. Yeah, I guess another thing, like from an educational perspective, I feel like sometimes it can be helpful to find, in general, to like find a set of documents that have a particular kind of thing in them, and NLP just makes it possible to ask more complicated questions instead of just like, does this have the word blah in it? Like, does this have a recommendation for a follow-up study in it? Does this have a recommendation? And you can ask questions like that to parse through like large amounts of reports quickly. For Jason's question, yeah, I think that's a really interesting question, and probably, the question is, how do you see NLP changing things in clinical workflow for writing clinical notes within interactions with radiology? That's more of a question for like me as an internal medicine person, or like, do you mean in radiology, or do you mean outside, like in other clinical contexts? I don't know how I can have Jason respond to me.
I don't know either.
Okay. He just put in the chat that he said up for interpretation.
Up for interpretation. Yeah, I mean, so I guess I feel like there's a lot of push. My sense is that there's been a lot of push both in radiology and outside to like try and structure data more, to try and have the writers of the data, like whether it's a radiology report or a clinical note, like structure it more in advance to say, either whether it's templates or whether it's using like checkboxes or drop-down menus, which I don't know about you, but I find like very unwieldy and like very time consuming, and also doesn't have the flexibility of natural language to talk as freely as you want about something. Like checkboxes are by definition like very limited. So I think like NLP kind of represents an alternate way forward of allowing, like the reason a lot of times people want that data structured is so that it can be automatically processed by systems, like by automated systems. And like, I think things like NLP can make it possible that we can still type with natural language, but they can still be but automatic processing, like big data analyses and stuff, can still be done. I guess that would be my answer. It doesn't force people to write in super structured or unfree ways, but still lets you process data in an automated large scale way. Yeah. Greg, that question is also very interesting. Have you thought about automating ordering of follow-up imaging using this tool? How big of a jump is that from this work? I mean, yeah, if you had a system with good enough performance and you just kind of wanted, I think most of these things, when it involves ordering routine imaging, like at least me in the internal medicine world, I just go by the radiologist's recommendation to order follow-up imaging unless I have like a very specific reason to say, like information that would change that. So I think in a lot of situations it might be appropriate. And I imagine for like outpatient follow-up of incidental findings and things like that, that could actually be a way to prevent stuff from falling through the cracks if you had a system with good enough performance. Then again, you have a lot of implementation difficulties with actually getting people to show up for those studies in the outpatient context, with like people who don't show up super often to appointments or people who like need a lot of help to get to appointments. I don't know, but I think it's a cool idea. For Abiola's question, robust multimodality representation. Out of curiosity, might you have data on the nature of the RECs, e.g. lung nodules, chest CT versus abdominal RECs? I do have that data. I don't know off the top of my head how it broke down, but I did try to include pretty much every type of recommendation, even if it was something like correlate with physical exam or sometimes people would recommend like a specific action, like diuresis. I remember I saw a couple of times. So, I think it's pretty broad. I was pretty broad and pretty liberal when I was like saying what a recommendation is to capture everything, but I don't have any of the numbers like memorized. So I can't really say more than that, unfortunately.
I'll ask you another question. Before we were talking a little bit about like model selection. Can you talk a little about why you chose certain models, or what was I think, did you say you tried a couple different ones? Like, what were they?
Yeah, different for the machine learning models. Yeah. During this kind of, this was kind of written at the time when transformers and attention-based models were really just coming out. Like I think BERT had just come out around that time, which is like one of the most, still to this day, one of the best general purpose like transformer architectures. But before that, natural language processing was all recurrent models, all like LSTM was basically the kind of the standard. One advantage of LSTM over transformer models is you can make a much smaller one that uses a lot less computational power. So a lot of times practically, people I feel like are limited from using things like giant transformers unless you're like a Google tier organization with specialized hardware for that kind of stuff. So, I mean, part of it was practical. And anything, I wanted to use in real time for like a software application, like we just didn't have the infrastructure to run transformers in real time. So that was part of it. And then part of it is that like, for projects like this, I feel like the data is the limiting reactant in terms of like making, like annotated data is very scarce. And so like any model is going to continue to improve as you annotate more data. And I don't know that we hit the point where transformers or more complicated models would have actually had a benefit over some of the simpler stuff like LSTM. So that was really the two major reasons that we went with LSTM. But I did try out a couple others. And for a couple projects like this, I found that transformers didn't really provide much of a meaningful gain for the amount of data we had, which is all hand annotated. So like was by necessity limited.
Yeah, so Greg made a comment in the chat, and I was going to ask maybe something similar, but he thinks maybe this could be used on like pathology reports too. Do you like what other sort of things? I know it said in the text about like getting findings out of the report. What do you think about that?
Yeah, no, I think it's a general purpose kind of mode for extracting contextualized information, and I think like the model, you could definitely use it for stuff like that too. You just have to annotate data that looks like that, because these kind of models are, again, very like data dependent. So it would probably require a separate annotation, manual annotation of that data. But I think the same methods could totally work. And in terms of other things in radiology reports, we did another paper that was trying to extract a bunch of different kinds of information besides just recommendations, like recommendations, imaging findings, like patient demographic data and stuff like that, just to see how far we could push it. And it seemed like the only real limitation is how long it took to annotate data. Brian Chang, what would be the next steps for bringing this model to other institutions/sites? Yeah, that's also a really complicated question, I feel like. part of it is that, you know, different institutions may use different, may have different data sets. So you'd have to annotate for different institutions. I don't think that would be a huge thing because it seems like there's a pretty broad representation of different ways to recommend things in this data set. So I don't think that'd be a huge deal. I know there's like complications about data privacy, you know, because you can argue that the model, you know, sharing the model that could basically in itself might have complications with like HIPAA or whatever, because the model is just kind of a function of the data. And like, there's a lot of situations in general machine learning world where you can figure out what data the model was trained on just by running the model, especially if it's a text generator. So, I mean, there are complications for it, but I think for the most part, it shouldn't be that difficult. Yeah, next comment. Is annotation of data something that can be democratized? Has anyone built a web platform like yours that can be shared, or was it custom built? Yeah, so like I custom built this one. Yeah, federated learning is another option, and we talk about it a little bit in this paper, and it's definitely interesting. In terms of democratizing annotation, I think that is, yeah, also a really interesting question. There are freely available annotation software. There's a lot of them have been like monetized and like you need to pay for and are proprietary and aren't open source. But I think like there are also some open source annotation platforms for natural language processing out there. When I was working on this, I just didn't feel like any of them had the power that I wanted out of it, and like, you know, my specific way of annotating stuff. Yeah. And I think as far as democratizing the annotation itself, I guess the only real analog I know of in the world is like how Google uses those CAPTCHAs, where a lot of the time when you're like checking how many, which of these have stop signs in them, you're annotating training data for Google's machine learning models. I don't know if I would call that democratization exactly, but it does kind of export the task to a lot of people. And I feel like there are ways to maybe do that. I don't know who would be doing the labeling. I think that, yeah, if there's a way to figure that out, get people to do the labeling as they do their daily workflow, that would probably be the only way. But also seems like a hard sell.
Looks like Tessa's in the chat. If anybody has a question for her, she'll probably answer in the chat.
Yeah, Greg says, question about HIPAA compliance is actually super interesting. Seems like there's a whole AI bioethics conversation to be had before we democratize AI tools. Yeah, I think it is really complicated. I'm not as familiar with that space, but I know there's a lot of conversations happening around it, both in like the medical space and general. Yeah, that's a good point.
Yeah, Tessa, we just had a question about whether if you took this model and took it to another institution, is that like legally allowed, or is that like a HIPAA violation? Like not even any of the actual like source reports, just like the model itself, since it was trained on this data. Yeah, that's sort of a similar conclusion we were having. Yeah, that's what Jackson said. Yeah, so theoretically, yeah.
Okay. Yeah, I think it's less of a problem with models that like do and like that extract data extraction as opposed to text generation, but I think it's still theoretically a problem that like you could reveal or discover the training data from the model operating. Yeah, my Felipe's question, do you think reports are more difficult to make HIPAA compliant than image data sets? My instinct is probably, actually, I don't know. My first instinct is yes, but I also feel like it's hard to make either of them like fully de-identifiable. I think we just need to have realistic rules about like what we've done to make things, you know, de-identifiable enough, because there's pretty much any information you can, like there's pretty, at some point, getting rid of any information, like you have to get rid of almost all the useful information to be able to make something fully de-identifiable. And there's all sorts of, there's like the whole, I think subfield in computer science of like differential privacy, which like has like mathematical guarantees on what it means to make, to make something private, and it's super complicated. Yeah, definitely agree with that too. I think making large public data sets and large public sets of annotation is like a super helpful thing that the field probably really needs, but is hard to coordinate.
All right, it's great discussion, everyone. Tessa's raising more questions about abilities to train AIs in a central repository, just how you access it or how you validate those models. Yeah, exactly. More questions than answers.
Yep, definitely true.
All right. Looks like we're kind of winding down. Oh, there's a couple more questions. How this model.
Right, Brian asks, how might this model fit into radiologist workflow if it were to be implemented? Would these recommendations be reviewed by a radiologist at any point? So I mean, like the recommendations were originally generated by a radiologist as part of the text, and we're just extracting that from there. But in terms of like what actually gets extracted, I mean, yeah, it depends on what the downstream use of them is, right? If it led to like the actual ordering of a study or the ordering of a biopsy, you know, ideally there would be someone who would be able to say, no, that's actually an incorrect, you know, because these models aren't going to be perfect. Some sort of check step. But I think that's like the advantage of, that's where like automated systems and human systems can really work, you know, complement each other's weaknesses, I guess, at this point, where like, you know, automated systems are really good at scraping thousands and thousands of reports in like 5 seconds and being like, these are possible places we should look at. And then humans can kind of review that subset. At least for now, while we have extremely flawed and difficult to interpret machine learning paradigms, which is probably going to be the case for a while. Right. There's so much like follow-up, so much lost to follow up on these incidental findings, you know, from a like primary care lens, especially. I feel like I see it all the time.
So I've had discussions before about whether models like this could sort of get out of whack, or like the training would not be as effective over time. Is that like possible in this model? Does it like learn while it's reading new things, or is it just kind of static?
Yeah, I mean, it'd be easy enough to build that capability in. We didn't specifically build that capability in for this, but we should be like, that would be a pretty easy change if we had kind of a continuous learning paradigm.
All right, I think we're pretty winded down. If anybody has any extra questions, go ahead and do it in the next 30 seconds to a minute. Otherwise, I think we're sort of discussed most of the things about this paper. It's a really great paper. I really enjoyed reading it. It's a cool model that has like a lot of application. It's really cool that it's worked so well. It's a good job, Jackson and Tessa.
Thanks for having us.
Also, once again, this presentation will be put online on the RFS section area in the website.
Yep, we should have the recording up by the end of this week. So thank you, Nate and Jackson and Tessa, for chiming in as well.